Beneath this sea, two countries are connected by a railway tunnel more than 50 kilometers long. This is the Channel Tunnel, linking Britain with mainland Europe beneath the English Channel. The route runs from Folkestone in England to Coquelles near Calais in France. The engineers were not simply digging through the ocean. They had to find the right rock. Too high, and the geology becomes difficult. The tunnel had to follow a carefully chosen path.
And the most surprising part is that the Channel Tunnel is not one single tunnel.
It is a system of 3 parallel tunnels, 2 for trains and a central service tunnel.
But could engineers working from 2 different countries meet beneath the sea with extraordinary precision? The dream of a fixed connection between Britain and France was much older than modern machines. One of the earliest serious proposals came from the French engineer Albert Mathieu in 1802. The early idea was very different from the railway tunnel that would eventually be built. For generations, the challenge remained the same: how to excavate beneath the dangerous sea.
There were attempts, proposals, and abandoned efforts before technology and politics finally aligned.
By the 20th century, the idea had become a serious international infrastructure project. The goal was simple to describe, but extraordinarily difficult to build: connect 2 countries by rail.
Before the machines could dig, engineers had to understand the ground they would be entering.
The route was planned through formations that could be supported with engineered tunnel linings.
Chalk and chalk marl became central to the route because the tunnel could be excavated there.
But the geology was not identical everywhere along the path. The French side encountered wetter conditions, making excavations slower and more demanding.
The machines could not rely only on their maps. They needed information from the ground itself.
The tunnels were designed to follow suitable strata rather than just a straight line. The deeper the crews went, the more important accurate surveying became. The engineers made a strategic decision. The smaller service tunnel would lead the way.
The service tunnel was excavated first, before the 2 larger rail tunnels.
It became a real-time geological scout for the rest of the project.
Instead of predictions, engineers could learn what the ground was actually doing.
That information could then guide the construction of the larger tunnels behind it.
In a project beneath the sea, information was part of the engineering strategy.
Then the machines began doing what human hands could never do at this scale.
At the front, rotating cutters attacked the rock continuously.
Behind the cutting head, the machine excavated, transported material, and advanced the tunnel.
The material had to be removed continuously so the machine could keep moving.
Behind the excavation, the tunnel had to be supported and lined with precision.
The project used both cast iron segments and precast concrete rings in different parts.
Every segment had to become part of a continuous, sealed, structural passage. The work could look repetitive, but every meter was part of a giant project. And this was not one construction crew moving in one direction.
The construction project commenced from both sides of the sea passage simultaneously.
6 tunnel boring machines worked from the British side.
Five more worked from France to meet them in the middle. 11 machines. 2 countries. 1 underground connection.
The crews were separated by the sea, but connected by a calculated route.
Surveying became one of the most critical parts of the entire operation.
The machines had to follow carefully calculated paths through the earth.
The closer the two sides came, the less room there was for error. Then, in 1990, the moment finally arrived.
The first breakthrough between the British and French sides happened in the service tunnel. A French boring machine and a British probe operation had reached the same point.
For the first time, the two construction efforts were physically connected beneath the sea.
And the accuracy was remarkable.
The alignment differed by approximately 358 millimeters horizontally and 58 millimeters vertically.
But the breakthrough was not the end. The 2 main rail tunnels still needed finishing. The largest part of the transportation system still had to be built. The 2 larger running tunnels had to be excavated, lined, and connected to the system. Cross passages created connections between the different tunnel sectors. Ventilation and technical systems transformed the passages into actual infrastructure.
A tunnel beneath the sea had to be more than a hollow space in rock.
It had to become a railway.
Power, signaling, communications, and operational systems had to work together. Only after testing could the tunnel become a working international connection.
But the engineers had another enormous problem. The tunnel produced massive amounts of material.
The question was simple: where could all of it go?
On one side, chalk was crushed, mixed with water, and pumped behind a barrier. The material was managed as part of a specially engineered containment system. On the British side, chalk marl was used to create a reclaimed coastal area. The material removed from beneath the channel became part of the landscape above.
From the surface, the English Channel looks like open water.
But far below, a hidden railway crosses the same barrier that once separated countries.
Passengers do not see the sea outside their windows.
They see the tunnel, while the ocean remains above them.
The 3 tunnels work together as one coordinated underground system.
The central service tunnel provides access and supports the maintenance of the fixed link.
What looks like a strip of sea hides a complex railway system beneath the seabed.
The undersea passage was officially opened.
The ceremony marked the formal opening of the fixed link between Britain and France. But the tunnel still had to become a fully working transportation system. Later in 1994, Eurostar passenger services began using the connection. The link could carry international passenger and freight traffic, plus vehicle shuttle services. The result was more than a tunnel. It was a new transportation link between countries. The difficulty of the Channel Tunnel was never just one single problem. Engineers had to understand the geology of the seabed floor. But the tunnel still had to become a fully working transportation system. They had to maintain the route with extraordinary precision over huge distances. They had to keep giant machines working reliably beneath the seabed.
They had to support the tunnel while it was still being created.
And they had to transform underground passages into a functioning railway. Today, the sea above the tunnel looks almost unchanged. But beneath it is one of the most ambitious infrastructure projects of the modern era. A 50.45-kilometer fixed link connecting Britain with continental Europe. Built by teams working from opposite sides, moving toward one underground connection. The astonishing part may not simply be that engineers dug beneath the sea. It may be that two sides, separated by water, met with measured deviation. A barrier that had separated Britain from mainland Europe became a route. Not above the sea.
Not across it.
But beneath it.
If you think building a railway beneath one sea was impossible, subscribe for the next project.